Alright, so next objective is objective 9, and we're actually going to cover objective 9 and 10 in this video. And we're going to look at solutions and pH. And so a solution is just a mixture. Alright, so it's important to understand that this is a physical mixture. It's not like a chemical reaction. They aren't chemically interacting. Essentially, we're mixing two substances together, but they are not chemically combined. And what that means is they can easily be separated. So if we were to dissolve salt in water, we could still evaporate the water out and the salt would be left behind. So they're not chemically interacting, they're just physically mixing together. Now, there are two parts of a solution. We have the solvent and the solute. And this can also be said solute. I think it's one of those things that's whatever you prefer. Honestly, I say it both ways. So we have the solvent and the solute. And essentially the solvent, most of the time, especially when we're talking about living cells, the solvent's going to be water. But the solvent is what actually does the dissolving. It's most likely going to be the liquid that we are putting something else in to dissolve. And then the solute is what we are actually dissolving in the solvent. So if you're making a saline solution, the salt would be the solute. The water would be the solvent. You mix them together and we now have a solution. Same thing if you were making a sugar solution, if you're making some sweet tea or some Kool-Aid, all of those things are just going to be solutions. And we have solutions inside of our cells and there's solutions outside of our cells. And those are going to be a water-based solution. The water will be the solvent and there will be many different solutes that are dissolved in our cells. And so a solvent, here is pretty straightforward. A solvent is going to be something that dissolves other substances. That gets dissolved, that would be the solute. Together they make the solution, and remember it's a physical mixture, not a chemical. Alright, so we're also going to take a look at pH in this video. And pH is when we're looking at whether something is an acid or a base. So we can say how acidic is it or how basic is it. Another word for a base or how basic it is alkaline or alkalinity. And so if you see that, just know it's the same thing. And so the pH scale ranges from 0 to 14. And really one of the main things you need to know is where do you find the acids and where do you find the bases. And so in the middle, here we have 7, that's neutral. And then anything less than 7 we would consider an acid. Anything greater than 7 we would consider a base. And so you can see some common everyday items. Things like stomach acid is down here, so it's definitely going to be an acid. Urine is going to be slightly acidic. Things like orange juice. A lot of times up here in the basic end you see cleaners. So soapy water, bleach, indigestion tablets. A lot of times when you're having issues with indigestion, some of that acid from your stomach is creeping up. And so we use those to kind of neutralize baking soda. Now pH is one of those things that we have to maintain in homeostasis because once again, we need our cells to be in relatively constant conditions and pH is going to be one of those conditions. And so let's first talk about acids. So as I showed you before, acids are going to be on the lower end. I don't know if it'll help you or not, but A comes before B in the alphabet. And so acids are going to be the lower numbers that come before the higher numbers on the pH scale. And so the lower the number, the stronger the acid. So just to kind of go back to that last slide. So here's neutral, where it's neither an acid nor a base. If I start going this direction, I'm getting more and more and more and more acidic. Okay, so the lower the number you see, the stronger the acid is. The same will be true for the bases. The further away you get from neutral, the stronger that acid or base is going to be. But acids are going to be on the lower end, and once again, lower equals stronger. Now, really what makes an acid is the type of ions that it's releasing in solution. So if something is an acid, when you put it in a solution, it's going to release hydrogen ions. And that's essentially what the pH scale is measuring, is the concentration of those ions. So we have another ion called hydroxide. And together, if we were to put those together, that would make water, which is neutral, okay? But here we have hydrogen ions, and so acids have lots of these. And so when it comes to the formulas, you'll typically see those H's in that formula like you see over here. And so the basic general formula is whatever your compound is or whatever your element or grouping is, a lot of times it'll have an H in front of it. Now, there are some exceptions, like up here, you can see some examples where the H isn't in the front. It's there, the H's are there, they just may be written in a different order. So here's acetic acid, here's another way that you could write acetic acid. But the main thing is when we put any of these things into water, any of these things go into a solution, they're going to release these ions, and that's what makes an acid an acid. The more of these that they release, the stronger the acid is. Now, bases are going to be the opposite, so they're going to be your higher numbers. They're going to be 7 to 14. Once again, the further away you go from that 7, the stronger it's going to be. So if you have a base that is an 8, that would be on the lower end, that would be a weaker base. If you had a base that was a 13 or 14, that would be a much stronger base. Now, they're going to be the opposite of the acids. Where acids released a lot of hydrogen ions, bases are going to release a lot of hydroxide ions. And the more they release, the stronger they are. And so kind of like with the acids, we have a basic formula. In this case, the OH comes second because it's negative. And so here's several different examples of some bases. And in each one, you see the OH in that chemical formula. All right, so 7 on the scale is neutral. And so just to kind of explain why, pretty much it's pure water. Everything else is either going to be an acid or a base. But at neutral, it's neither. It's neither an acid nor a base. And so the reason pure water is neutral is because if we were to break that down into ions, so hopefully we know that this is the chemical formula for water, H2O. And so if we were to break this down into its ionic forms, we would get an H plus and an OH. And so you can see that they kind of balance each other out. If it's an acid, it has more of these. If it's a base, it has more of those. But if they're equal, that means it's going to be neither an acid nor a base. And so pure water fits in that category. And our pH in our bodies is going to be close to neutral. Okay, it's going to be slightly on the basic end. And so because we do have so much water in our body, our pH is going to be kind of around this neutral range. But that's why pure water is neither one. It's because those ions kind of equal out. All right, so which of the following pHs would be the least basic? Okay, so remember that basic are your bigger numbers. A comes before B. So acids are less than 7, bases are greater than 7. And so obviously this right here, high number, that's a very strong base. 9 would be a base. 7 is neutral. And 3 would actually not be a base at all. It would be an acid. So that's going to be our answer there. And then which of the following is an acid? So what we're looking for are going to be the H's. Okay, remember in the basic formula. And so here we know it's not this one because there's an OH. That one's for sure going to be a base. This one doesn't have either one. And so this isn't meant to be tricky, but here we have HOH and H and then bromine, I'm pretty sure. It's been a while since I've done my chemistry. And so here, this is essentially, it's not meant to be tricky, but HOH, once again, that's water. So that one wouldn't be an acid or a base. And so in this particular set of examples, there is my acid, okay? All right, so there's going to be one more thing that we need to cover for pH, and that is buffers. And buffers are solutions that have weak acids or weak bases. And what's important about a buffer is it helps resist a change. So if you were to add a strong acid or a strong base to a solution, it's obviously going to change the pH of that solution. But if we needed that pH to stay the same, then we could use a buffer. And so what it does is it helps to keep pH at nearly a constant value. So this is going to be important in our bodies in terms of homeostasis. because we don't want our blood pH to be changing. We don't want the pH of our body fluids to be constantly fluctuating. And so we have buffers like in our blood and in our body fluids that help to keep our pH at a constant level. You can see down here that like our blood pH is slightly basic. It's a little bit above neutral, okay, around 7.3 to 7.4. If we start going outside of that range, it doesn't take much for us to get sick or possibly die. And so maintaining that blood pH and maintaining the pH in our cells is incredibly important. And so what the buffers do is they just help resist those changes. So like over here in this example, we have an unbuffered solution and a buffered solution. They both have a pH of 7. And if you were to add an acid to each of them, this one greatly lowers the pH because it doesn't have a buffer in there. But over here with the buffer, it does change it very little, but it's not near the change that you see over here. So buffers help us to kind of resist changes in pH and kind of keep a constant pH. And once again, that's all about homeostasis. It's something we definitely need in our bodies. And so which of the following describes a buffer? It's definitely not a strong acid. It's definitely not a strong base. They're either weak acids or weak bases, but they do resist a change in pH. And that is going to wrap up those objectives.